guys remember? Well, what is blood? What is a term that we use for blood? Heme, right? And so now, instead of doing what's called homeostasis, where we just are regulating different variables in the body, specifically we're talking about making sure we have enough blood in the body, or we don't lose blood, okay? So it's called hemostasis, okay? So preventing blood loss is called hemostasis. And in preventing this blood loss, hemostasis, there's really overall three big things that are going to play a role in this. What are some of the things you can think of right away?
Vascular spasm.
Okay, the condition of a blood vessel plays a role. If your blood vessel wall is compromised, that blood vessel can then tear. So condition of the blood vessel wall will play a role in this. So
hemostasis is a normal.
yes, hemostasis is preventing blood loss. But when we're talking about problems with hemostasis, the things you're going to be looking at is the condition of the blood vessel wall. Okay? Is one. What else would you maybe look at? What else is going to play a role in making it to where you're not going to lose blood?
Platelets.
Platelets. Okay, you need normal platelets, and you need a normal amount of platelets in your blood if you do tear that wall. So platelets are important as well. And then there's one other thing. So once you have a platelet plug, what happens?
Fibrin and
Coagulation. And when we're talking about coagulation, what's really going on after you've formed this plug? What are you doing? What's happening in that blood? Cascade. It's a chemical cascade. You have these inactive proteins that are circulating in your plasma of your blood, and then you get a tear, and then they're going to start to get activated, and you're going to have this cascade of chemical reactions that are going to lead to a final product that is insoluble. It's going to precipitate out of that solution and kind of create a Band-Aid inside of that torn blood vessel wall. So the other thing that you can think of that might affect just normal hemostasis is if you have a problem with these coagulating factors and enzymes.
so like intrinsic and extrinsic factors.
That's some of those coagulating factors. You also have a common pathway to those, okay? I'm going to just call them in general coagulating proteins, because really that's what they are. The disorders or diseases that we have in regards to coagulating and clotting is, hey, we got something wrong with the blood vessel wall, all right? Oh, something's going on with these platelets. Or you have a protein that is not the proper protein. It's a mutant form of the protein. It doesn't do its job, okay? So, and the other thing that could happen with these, if you have something wrong with that, is a diet thing, because a lot of these coagulating proteins need vitamin K, for example, for them to actually function properly. So if you have a lack of vitamin K, that could cause problems in hemostasis. Now, as George was saying, the very first thing that's going to happen is a vascular spasm. So we're going to go now through what normally happens to prevent blood loss, all right? You get a tear in your blood vessel. Because that's what we're talking about, is an opening in the blood vessel that now blood is going outside of the body. So the first thing that your body's going to do to make it to where you are losing less blood is that smooth muscle, that blood vessel, is going to contract. So let's say the tear is like this. This right here, this, that's the tear. But you have a vascular spasm, and now that opening is less. So that's the first thing that's going to happen to slow down that blood loss, a vascular spasm.
It'll also decrease the diameter of the lumen too, correct?
Well,
And
yeah,
vascular
I mean,
spasm?
that's vasoconstriction. But the thing is to bring that tear part closer together so less blood is going outside of the blood vessel. At least that's how I view it. So you're going to have a vascular spasm. Now, what happens when you have that tear, what's being exposed is these collagen fibers. What is collagen? What kind of molecule is collagen? It's a protein. So you're going to, when you have a tear, you're going to see that collagen fibers are exposed. And collagen is a protein. And proteins, for the most part, have a negative charge. Okay? And in part, this negative charge, and also a factor that's called von Willebrand.
DWF.
Proteins have a negative charge, and you have this thing called von Willebrand. I don't know if I'm spelling it right. Is also going to be exposed, all right? Now, the thing that makes this important is that this negative charge and this von Willebrand factor being exposed from that ripping, platelets are going to want to go towards it. Okay, so that's what's going to make it to where these platelets are all, ooh, I want to stick to this, all right? So that's the next thing that's going to happen is you're going to get a platelet plug, all right? And in part, that's because this platelet is attracted to these negative proteins, these collagen fibers that are exposed, and it's going to, a protein on the outside of it is going to want to bind to this other protein that's being exposed. So we're pretty good with that.
Can you repeat that one more time?
Platelets want to, they're attracted to negative charged things. And proteins are negatively charged. So they're going to want to go to this area, the wall that has been torn, and now the collagen is being exposed. They're going to want to go towards it. But you're also going to have these molecules called von Willebrand that are also there, saying, come on, platelets. So think of it this way. Here we have a tear. This over here is normal. And this is like the lumen of that blood vessel. Okay? So everybody's picking up what I'm throwing down here a little bit?
Yep.
Okay, cool. And then this tear, you have now collagen being exposed, which has a negative charge to it.
Because it's hanging out in the subendothelial layer, correct?
Right,
That's
because
now
you
exposed.
torn this, and now it's exposed. Also, you're going to have, I'm going to just put this as VW, just to simplify it. You also have VW being exposed. Platelets, I'll do a different color there, are attracted to that. And so they're going to start to be all, ew, ew. Okay? Oh my goodness. Does that help? Okay. Now, so you're going to start to form this platelet plug. And I'm going to elaborate a little bit on this right now. Okay? Normally, when there isn't a tear, platelets don't just stick to the wall. And the reason why is that nitric oxide is being released in that blood vessel. And nitric oxide actually makes it to where platelets don't want to stick to the inside of a blood vessel wall. It prohibits that from happening. And so that's why you don't get these platelet plugs happening with just normal flowing blood. just in general, nitric oxide says, it stops the platelet from doing that. So everybody go with that.
So there's
So that's what's gonna happen normally. But then, when you have a platelet plug and it binds to collagen and von Willebrand, these platelets are gonna release, degranulate, because all platelets are is a fragment of a megakaryocyte in the bone marrow, big, huge cell with a big nucleus, rubbing up against reticular fibers in that bone marrow, and then little chips of that megakaryocyte come off, that's your platelets, and they go into circulation. They're gonna last 10 days. They're very short-lived, all right? And you have a certain amount in your body, like 150,000 to 300,000 per millimeter cubed in a volume, right? But when you have a tear like this, when they bind here, they're gonna degranulate, just like the mast cells degranulated in hypersensitivity 1 and released histamine, right? Instead of releasing histamine, these platelets are gonna release ADP and a thing called thromboboxane? Did I spell it wrong?
Thrombin, right?
Almost bonding.
Thrombospondin.
Huh?
That's what this thing says. I don't know.
TXA?
This is the wrong book. This is not English 101. Wrong class.
Thromboxane. This is right. They're gonna release other ones. I'm focusing on these ones, okay? And the reason why I'm focusing on these is because we're gonna see that these platelets are gonna do contraction and need ATP and all that to contract, and they have actin later on in this process. Also, I use thromboxane because the name of platelets are thrombocytes. Makes sense. This whole thing with coagulating, we think of thrombosis and thrombocytes and
Thrombocytopenia.
right, which you know what I'm saying, low platelet count. So I'm trying to keep in line with this thrombo term here. Everybody's so good. Okay, cool. All right, so these platelets are going to release, degranulate, and release this. All these guys are doing is doing like a chemotaxi. They're signaling for more platelets to come in, right? And so now more platelets are going to be all, ooh, yay! And they're going to start to create this plug. All right? And if we're talking about like a minor tear, a lot of times the platelet plug is sufficient. But if you start to get more of a tear, you're going to want to go to the next step, which is what? Anyone? Anyone? After a platelet plug is formed, what happens next? Coagulation, right? So this is the thing that happens there. And then the next thing that's going to happen, ooh, I wonder if this works. So this is 1, this is 2, and then 3 is coagulation. All right? And coagulation is going to be where we have all these coagulating proteins having a chemical reaction in a sequence to form fibrin, which is going to eventually be this fibrin mesh that's sort of like a band-aid on this tear, okay? That's what's going to be the end result. So the end result of this coagulation is a fibrin mesh. circulation and getting to that fibrin mesh, you have three pathways. You have an intrinsic or an extrinsic. And both of these are going to lead into a common pathway. Right? The common pathway, if you've taken AMP2, you already know to some extent. So let's go backwards and do the common pathway here. We're ending with fibrin, right? But what was fibrin before it was activated? Fibrinogen. And what was the enzyme that activated this inactive protein to precipitate out of plasma to form this mesh? What was it? Thrombin. Right? Good? And what was this enzyme when it was inactive? What was its name?
Prothrombin?
Prothrombin. And then we had prothrombin activator. This is the common pathway here. Okay? Now, in your book, there's this thing called proacelerin. That's prothrombin factor.
So it like accelerates the whole process?
It's just an enzyme. It activates prothrombin to becoming thrombin. This is something you already are familiar with if you've taken AMP2. If you haven't taken AMP2, unfortunately, you have to get this in your head.
Was it called again?
sucks.
Proacelerin?
Yes, proacelerin. It's the same as prothrombin. That's how we know it from taking AMP2. All right? Everybody still good with that? Okay. Now, what really starts this common pathway is a molecule called Stewart-Crowder. I don't know why it's called that. And I'm fine with you knowing the names of these or the numbers. I don't do well with numbers. So if you know that Stewart-Crowder is 10 and these other ones have their little numbers, that's acceptable to me. So you could do it either way. Because I understand that some people are better with the numbers, the Roman numbers. I do better with the names.
Will it be either way on the exam?
Yes. So I would have something like this, Stewart-Crowder.
And then I'll have like parentheses or something.
Yes. Okay. All right. So the intrinsic and extrinsic factor are ultimately wanting to get to this one that starts off the common pathway. All right? Now, we are already familiar with intrinsic and extrinsic, those terms, correct? So which one of these is dealing with stuff that's already in the blood?
Intrinsic.
Intrinsic. So this one is dealing with something that's outside of the blood. And in particular, it's dealing with something that's in tissue, or a part of this wall here, called tissue factor. So you have like tissue factor in that connective tissue that makes up that wall of that blood vessel, right? Versus these intrinsic factors that are part of the intrinsic pathway are dissolved in plasma, okay? They're dissolved in that watery solution. Which pathway do you think then, based on this information, you got tissue factor in the wall, and you got these already in the plasma, which one of these is gonna get triggered to occur when you have a much bigger rip in a blood vessel?
Extrinsic.
Extrinsic. Because that means that you really ripped that blood vessel wall, and now this tissue factor is moving from that wall into the blood itself and playing a role in this pathway. So this is going to be dealing with major trauma. This one is going to kick in. Everybody still good with that? Major trauma here.
The tissue factor is in the wall.
Right. Tissue factor is going to be part of the coagulating pathway for the extrinsic pathway, and it's outside of the blood. It's in the wall of the blood vessel instead. Everybody good with that? Or within the connective tissue that capillary blood vessel is within, all right? It's within connective tissue, all right? But this is where you're going to have major trauma, all right? This one here is a little tear. Little tear. Which one do you think is going to go faster? Which pathway?
Intrinsic.
What?
Intrinsic?
Which one are you going to be bleeding a lot more?
Extrinsic.
This one you're going to be bleeding a whole lot more. Do you want this one to go faster?
Well, you want it to go faster.
You want it to go faster, and it does, all right? So this one here, you're bleeding more. And we're going to find this actually has like one step or so, something to it. It's very quick, one step. Boom, this tissue factor is going to combine with, it's going to activate another one of these coagulating things to making this.
So it's kind of like C3, how you have that alternate pathway that just starts off
Yes.
right away, rather than having these million steps to go through.
Correct. So this is, you're bleeding more, you really have like one step or so, and you get this common pathway to start making this. So this is faster, and you want it to be faster. So calcium and tissue factor are going to activate this thing called proconvertin. All right? That's the extrinsic pathway. Boom. This intrinsic one, it's a small tear, and it has a lot more steps. It is going to deal with this thing called the Hagman factor. And then we're going to get into, I know Christmas and anti-hemophilic factor. And then there's this really weird one that's called plasma thromboblastin antecedent. Plasma thromboblastin antecedent. This is another. So here, go here, go here. These are all going to get activated type of situation. Then you're going to have Christmas factor. And then you get this anti-hemophilic factor. Calcium is going to play a role throughout all of this, activating factors and stuff and get them all prepped. But these guys then are going to okay. But this one has like so many more steps. It's going to take longer. But it's okay because that's a slight tear. All right? You guys good with that? Yeah?
Wait, so what are the steps for that? The blue one.
The red is the extrinsic pathway. The blue is the intrinsic. which is slower, more steps. They both are going to lead to this common pathway. Okay? Other questions? So some of these coagulating proteins, well, first of all of these, where do you think they're made, other than tissue? What?
Can I ask a question?
Yeah.
So the intrinsic and extrinsic pulse lead to the Stewart-Crowell or Stewart-Crowell lead?
Yeah, the beginning of the common pathway. They're both going to go to that common pathway. It's just they're going to get there in different ways. One takes essentially one step. The other one takes 4 steps. The reason why the extrinsic one takes 4 steps is because tissue factor is now going in to that blood where it wasn't there before. But you've had such a big tear that from diffusion, it's going right into the blood. It's going to combine with calcium, and it's going to activate proconverted, which then automatically activates Stewart-Crowell. But if you don't have such a big tear, and it's just tearing a little, you're going to have Hagman get activated, all right? And these are getting activated in part by what's going on with this platelet plug here, all right? And then that is going to have this cascading effect where you're going to start to activate all these other ones. And then you get into the compound. This is going to take a lot longer just because there's more steps. You're not bleeding as much, so that's nice that it takes longer versus the one where you're bleeding more. You wouldn't want that one to take longer. You want that one to be faster. Are you good? Are we picking up what I'm trying to? Okay. Other questions?
So is it the parietal cells of the stomach?
Well, let's think about this. We're talking about these factors being where in the body? They're in the blood, right? They're dissolved solutes in plasma. When we think about proteins in plasma, what organ or gland do we think of as making those proteins? What is the most common protein in plasma?
Albumin?
And what makes albumin?
Liver.
Liver. Guess what makes all these?
The liver.
Yeah. So all of these, except for, I want to say this one maybe. One of these the liver doesn't make. I'm not going to really ask you a question on that. But almost all of these the liver makes, okay? In that inactive form. Because all of these are in the plasma, but they're not activated yet. You have to tear a blood vessel. And then they start having this chemical cascade, all right? When we're talking about hemophilia, that X-linked recessive disease, I'm sure most of you are familiar with that. That is a consequence of someone not making either Christmas factor, they have that gene that codes for this particular factor is a mutated gene, they don't make the right protein here. Or anti-hemophilic. That one makes sense, right? But either one of these, and you could have hemophilia, all right? Also, other things to consider is like vitamin K. Vitamin K is important in the making of these proteins, and the ones that it's important for is Christmas, vitamin K, check. Proconvertin, check. Prothrombin, check. It needs vitamin K. And Stewart-Crowder, check. So if you have a vitamin K deficiency, you're going to have problems in all of these pathways. Okay, so having vitamin K in your diet is important. Is vitamin K a water-soluble vitamin or a lipid-soluble vitamin? Okay, I have a way for you to remember all the lipid-soluble vitamins. I say A-Dick. I mean, I honestly am not trying to be... Those are all your lipid-soluble vitamins. Okay? All right, vitamin A, D, E, and yes, K. So if you don't have enough lipids in your diet, because this is a lipid-soluble vitamin, you're not able to absorb it properly. So that could be one of the reasons why you don't have enough vitamin K to make these coagulating. It's just not having enough lipids in your diet. Or not producing bile, enough bile, to break down those lipids that are going to surround these vitamins to allow them to go across that cell membrane and absorption, okay? So not being able to make enough bile can lower absorption of vitamin K, okay? So you've made your fibrin mesh. The last thing that's going to happen here is what's called a clot retraction. Clot retraction is essentially, what color should I use for that? Orange. These platelets have actin in them, and so they're going to contract. And as they contract, it just makes it to where this whole thing with the platelets, the fibrin mesh, just gets tighter. All right? Now, do you want to ultimately keep having this thing going and going and going? No. So you're going to want to actually start eventually to break down this fibrin. So this is where, hey, you've stopped bleeding. You've successfully stopped bleeding, all right? But you don't want it to be where you stop the bleeding. So this is like a cross-section of a blood vessel. You have, that little platelet plug, getting this fibrin mesh going on. But if you didn't stop this, this would start going like this. We don't want that, right? Because then we're going to get an occlusion. So we want to, after we've actually prevented blood loss, we want to start to break down that fibrin and to stop it, all right? And the way that's going to happen is with another molecule. And that molecule that starts to break down, and this process is called fibrin Fibrinolysis. These are lysing apart that fiber. Fibrinolysis. And all that happens here is that plasminogen, which is going to be, start to get released here in this whole mass of platelets and fibrin. It'll get released, stuff like this Pagmin will trigger its release. Right? Certain molecules are going to trigger the release of this particular protein that's inactive. And then this protein is going to get activated into plasmin. And plasmin just starts to cut this into little bits, right? And that's needed so that you don't have this continually going on and then you actually block blood flow in that blood vessel. What do you go with that? You have like 5 minutes, I'm gonna let you go though. Next time what we're gonna do after the quiz is I'm gonna give you this sheet of the different disorders with this, and they actually do laboratory tests to figure out what kind of blood clotting coagulating disorder you have. And so I'm gonna brainstorm on maybe some case studies
So like
to work through
PPT
those.
times and stuff like that?